now see exactly how to compute the semi-dominator and the immediate dominator. After that, in a separate video, we will see the pseudocode for the Lange-Artarian algorithm and then an example. Okay, recall that the semi-dominator is the smallest vertex, V, such that there is a path from V to W with intermediate nodes with higher depth of search numbers than W. Okay, so the question is, how far should we, obviously we have to search from predecessors and upwards, and the question is, how far should we search? And more practically, how can we stop the search from going all the way to the start vertex? For 5, we evaluate 4 and 7, and we want to find, well, we want to find 2, but when we search from 7. So what we do is to search the value of the parent attribute, but we save it in a separate variable of already, okay, this separate variable is called the ancestor. And we process the vertices to find the semi-dominator starting with 7. And we find that it is number 6. And then we process number 6 and find that its semi-dominator is 2. Then we go and find the semi-dominator of 5. That means we have not found the semi-dominator of 2. Okay? And we have not set the ancestor attribute of 2 to 1, but we have set the ancestor attribute of 6 to 2. That means we can follow this way back and find we look for the ancestor starting from a predecessor with the smallest semi-dominator. Initially, the semi-dominator is set to a node itself. The effect of this is that when we search from 7, we will conclude that 2 is it's a candidate for being the semi-dominator of 5. Okay, so this timing is crucial. I mean, the timing of setting the ancestor attribute to be a copy of the parent attribute so that we do not search too far. Okay, so when we do the depth first search, we put all vertices in an array in a way so that we can process the nodes, I mean the vertices, in decreasing order of depth first search number. And we have a function which finds the ancestor with least semi-dominator. This is called eval. Okay? And there is another function called link, which copies the parent into the ancestor attribute. And that is called after we have found the semi-dominator. Okay, so how do we do? We start with searching each predecessor using eval, and then we take the one which gives us the smallest vertex as the semi-dominator of W. Okay, a different, the purpose of this is to find the immediate dominator. And as you recall, we use the semi-dominator to determine if the semi-dominator is the immediate dominator of a node. So, for instance, we are interested in determining to find out if 2 is the immediate dominator of 5. As an example. And we do that by searching from 5 up to 2 at some moment in this algorithm. And what we will come to now is at which moment should we do that search. it turns out that we can do it when we have processed a child of 2. That means, when we have processed a child of 2, then we can process all nodes which have 2 as their semi-dominators. Actually, all nodes which currently have all current nodes which have 2 as semi-dominator. Okay, so okay, this might be a little bit unclear. What we have at one point, it's 6 which has 2 as semi-dominator. Then we process all the children, all the nodes which have 2 as semi-dominator. So we process this one. And then at another time, we have 5 as a node with 2 as semi-dominator. So there are we process all nodes with a certain semi-dominator and at multiple times. Okay. What we have to keep track of those nodes which have a certain semi-dominator is to have an attribute bucket, which is a container, just a set, a linked list of nodes in each node. So each semi-dominator has a bucket of nodes which have that node as the semi-dominator. So what I'm saying is that when we have processed, for instance, 3, at that point, 5 is in this bucket. And we process each node in the bucket, and actually it will be only 5. And what we do when we process it, we search upwards to the semi-dominator. And then we follow the parent attribute from the depth of search tree. Okay, so when we follow this, we discover, for the case of 5, that there is a node with a smaller semi-dominator than 2. And it turns out that the node with the smallest semi-dominator on this path from 5 to 2, its immediate dominator is the immediate dominator of 5. That means the immediate dominator of 5 is equal to the immediate dominator of 3. But we don't know the immediate dominator of 3 because we have not checked that part of the graph yet. So what we can do is to save 3 for later use. The important thing is that we know that the immediate dominator and the semi-dominator are different. If the semi-dominator and the immediate dominator are the same, these variables, this is okay, then it is the correct value. But if they are different, then we should take the immediate dominator of the node saved as immediate dominator and use that as the immediate dominator. Okay, that means okay, so we search upwards, find the node with the least semi-dominator, we can call it U, and eventually when we know the immediate dominator of U, we can set the following. But we don't know the immediate dominator of U yet, so we have to do that in a fourth pass of processing the vertices. Okay. So you can check this summary of notation. And